think I've ever seen it published or shown before. And a friend of mine, Dale Parfett, who was the PAR and PAR antennas, I talked to him about it and sent him a bunch of information, videos and things. And he got back to me and said that he'd never seen anything like it. And he builds STLs and sells them, as well as various antennas for hams in the military. So he would know, he's an engineer in that area. So as far as I know, it's not a widely known thing, although it might be by now. And undoubtedly that self-resonant loops isn't a brand new idea. I've seen them used in microcircuitry and such. But so let me see, what else was I going to make sure I said here? One of the things that has been useful is the discovery of this PEX-LPEX pipe, which I use to make all these. It's a very nice material for building loops. I was building receive-only loops. LZ1AQ has a nice design and has a lot of information online. And he used this pipe that I'd never heard of called PEX-LPEX pipe. And this is his picture over here. So I built some of his receive loops using the same material I bought from Amazon for about 25 cents a foot. PEX-LPEX pipe is PEX is a commonly used plumbing pipe. Most modern plumbing is with PEX, cross-linked polyethylene. And it comes in different colors and it's used in most of the new housing. This is a different version in that it has an aluminum tubing embedded into it, an aluminum tube embedded into the PEX. So there's a layer of PEX on the inside and a layer of PEX on the outside of the aluminum tube. The aluminum tube is about 0.2 millimeters in diameter. And it's there because this pipe is used in heated flooring, and this is an oxygen barrier. So it prevents oxygen from diffusing into the pipe. And that apparently corrodes the pumps and the hot water heater and such. So that's where it's used. It's available widely. Again, metal with the inner and outer layer of polyethylene and some adhesive here. Polyethylene, Dale tells me, is probably the best dielectric for HF frequencies. It produces a lot of capacitance when it's put between two conductors, and it has a very high breakdown voltage, so a spark doesn't jump through it very easily, which is what we want to see here. So this was used in all my loops. There's no reason why it has to be used, but it's got a number of advantages. I noticed that some people were using this PEX-LPEX pipe to make small transmitting loops too. They were improvising capacitors, like a piece of coax stuck inside it, or a shaved down smaller size of the PEX-LPEX pipe going into it, or even a hacked up piece of PEX-LPEX that slides in. But these people were making these things into transmitting loops instead of just receiving loops, and they were working for them. So I decided to try it too. So I built a 20-meter single turn classical loop with the feed loop at one side, a capacitor at the other side, sort of a homemade design, and tested it versus my antenna's end-fed wire, and it worked pretty well. I was pretty happy with it. This is the normal classical small transmitting loop design that you guys are probably familiar with. It's a single turn loop. It's got a tuning capacitor, either an air variable or, for higher power, a vacuum capacitor, and a feeding loop that makes a transformer coupling with this larger single loop. 100% efficient transfer of power. Your transceiver is then connected via coax, and this is sort of a circuit design. We can come back to this later. The rule of thumb for these single turn loops is that you want the length of the conductor to be between 1/8 and 1/4 wavelength. And so that's how I decided how long to make mine. Even though that rule is to apply to single turn loops as opposed to multi-turn loops, it's a place to start. So a friend, Tom, K7XSO, came to me a year and a half ago, and he wanted a small loop for 40 meters he could take on his motorhome. He wanted to check into the Beehive net, and he wanted to have something he could take around with him and put on the roof of his motorhome and to transport it. So I decided to make them a 2-turn loop, and with a regular capacitor, a classic design. I built it, but I could never get it to resonate low enough. It always was resonating too low. I'm sorry, I could never get it down. I took a piece, I wrapped it up, I put the smallest capacitor I could build. It was still too low. I cut off 2 inches, still too low. Cut off 6 inches, still too low. Cut off a foot, still too low. Finally, I gave up and said, I'm going to just try it without the capacitor. So I jiggered it around to get it to resonate within the 40-meter band, and I tried it out, and it worked pretty well. So here's sort of an explanation of the capacitance and the tuning. This is a two-turn loop. This is all one piece. These loops, the transmitting part is just one part. It's just a piece of pipe. There's nothing else there. There's the supports and the spacers and things like that, but it's just one conductor, which is very good because you don't have the resistances introduced by soldering and mechanical connections to the vacuum cap and all that. So it makes it a very efficient loop. And you can see here, if I took this 13 feet of pipe with 1.5 millimeter spacing between the turns, I got a resonance at 15 megahertz. When I did 3 millimeter spacing between the turns, the resonance was now 16 megahertz, up 1.1 megahertz. When I went to 5 millimeter spacers, it went up to 17.2, another 1 megahertz up. And then finally, I went to 7 millimeter spacing. You see how widely spaced this is now. And it went up to a 19.1 megahertz I'm talking too fast. It was resonant on 19.1 megahertz. So by changing the spacing of this pipe, you could tune it up and down the band quite considerably. So I went back to Tom's loop that I was building for him and put a piece of Teflon pipe into the end of the pipe, put my foot on it to hold it in place, and set it for the bottom of the band. And then I pulled it down with my foot on it again and pulled it till it went to the top of the band. So I realized this would be a way to tune it. This would be some way to tune this thing, because I didn't want to make a loop for just one frequency, and it would always need some tuning. So I built some machines, some different screw things to try to make this a more precise way of doing it. But this is the basic idea. By pulling the tuning arm away from the main loop, you change the capacitance between these two lines. And the further you pull it away, the lower the capacitance, the higher the resonant frequency. So these were all built with that type of tuning. Here's the arm that pulls it away right here, and this is the machine screw that pulls it away. That's 70. Here's this 20 meter, 40 meter has got, this is Tom's antenna. This is the 40 meter antenna. 60 meter screw here, stepper motor version here on the 80 meter that can be controlled from remotely. I'm going to show you some audio now, play some audio from this antenna right here. This is the Beehive. Loop, then wire, loop, then wire. How do you guys get familiar?
K7 ET. Thanks, Daryl. AF7Y. W6AIL. W6AIL. No traffic, Tom. Thank you, Howard. K7TM. W7MZB. Hi, Tom. W7MZB with no traffic. Thanks, Val. M7.
Now this is the end-fed 130-foot wire.
W7CMS, St. George, nothing from here. Good day, Tom.
Now we go back to the loop.
No traffic, and I have two for you, Tom.
All right, Bob, thank you. W7DTO. W7EKG. W9LF. K7 Charlie Fox. K7 Charlie Fox.
I love that guy.
Thank you, Mike. K7NX. K7NAL. K7NR. Traffic.
Yes, Tom, 87SR, no traffic.
Thanks.
Now we're back to the wire. Now, not all days show that profound a difference, but some do. This is another method of tuning the loop. So this is the main transmitting loop here, and this outer loop rotates around it. And when it's at right angles to this loop, it has very little influence on it. But as it rotates into the plane of the loop, it changes the resonant frequency. So this is an outer changing loop. And this one's the same thing, but with the loop on the inside turning. I'll show you more on this later. I'm going to skip this one here. The bandwidth of a small transmitting loop is inversely proportional to its efficiency. So the narrower the bandwidth, the better efficiency. This is the bandwidth for 20 meters is 21 kilohertz. 40 meters is 9 kilohertz. Let me see, what is this? 60 meters is 7 kilohertz. 80 meters is about 5 kilohertz. And I made a very big, very narrow bandwidth 160, which was 3.6. The point I'm trying to make is these bandwidths, if they were for single, regular, classically designed loops, would indicate a very high efficiency. The other point I want to make is that in the 80 and certainly the 160, it gets hard to squeeze a single sideband signal into the sweet spot on the SWR. So this was the tuning I used to go to 3.863 lower sideband. I actually tuned the antenna down 1 kilohertz so I can drop the signal into this, the cradle here of this bandwidth. So, and when you got down to here, I had to use the narrow bandwidth on the transceiver. So there are some sacrifices you make, but this works very well, and their efficiency would be predicted to be fairly good. I'm going to now switch to the video, and we'll stop for questions. Is there anybody that wants to interrupt here? Not hearing anybody. I'll try and share this now if I can figure out how to. Up here. I'm going to stop sharing, and then I'm going to share again. And this time I'm going to go to the video. I'm going to share that with audio. And let's go here. So this presentation, I'm trying to be very pragmatic and show you exactly how these things are made. And so that's what it is. And these are the multi-turns loops. I hope it streams reasonably, and again, chime up. Here we are in my garage with questions, with the basics of the loop. This is a example here. They're all made pretty much the same. I'll show you some differences later. This is a 20-meter loop. It has a number of components. First of all, there's the PEX-L PEX pipe. You can see there, the red pipe. There's spacer clips here, 3D printed. Let me see if I can get it to focus. 3D printed spacer clips. Supports, here's a 3D printed, somewhat rainbow colored 3D printed support that helps hold it onto the military 1 3/4 inch fiberglass pole, which is supported on a piece of wood down here. So that's the lower clamp to give it a little bit of support from below. And then there's an upper clamp here, which you can see, that one, that holds the top of the loop in place. Sorry if they're a little out of focus. And then there's the feed loop, which couples the signal from the transceiver into the transmitting loop. The feed loops I use are all sort of one size fits all, and that size is way too big for a 20-meter loop, so I have to overlap it a bit. By moving this feed loop up and down on this pole, I can adjust it until I get a 1-to-1 SWR. Always been able to get a 1-to-1 SWR, so it seems to be a very reliable system. And then, in addition, there's a tuning mechanism. This is what I call the tuning screw. I've made up these terms. So, and what it is a machine that's a threaded bolt with some 3D printed parts. And as I turn this part, it separates the black pieces or brings them closer together. And what that does is separate or bring these pieces of pipe closer together. And that adjusts the tuning across the whole 20-meter band. The spacing generated by these clips here determines where the resonance of this loop is. So if I use smaller clips with smaller spacing, the loop would be at a lower frequency. If I use thicker clips, wider clips with bigger spacing, the loop would resonate at a higher frequency. So the diameter of the loop, the amount of spacing between the turns, and the length of the pipe, of course, interacts there to tell you, sorry about that, to determine the place the loop resonates. When I build them, which I'm going to do in a minute, I'm going to build one of these, you get a cut a length of tubing, and I'll tell you how I get my first approximation of what the length should be. I'm going to call it alternately tubing or pipe, but technically I think it is pipe. It's called PEX LPEX. I think I've described that already. There is a supply of it. It's the red tubing, not the white tubing, and there's the 1/2 inch on top and the 1 inch size. So here we are again looking at the spacers, and right here. Again, there's a 1, 3, 5, 7 millimeter spacers. I had a number of systems that I used before. These are by far the best. They have a nice system of just snapping. So you heard that snap and snapping. Makes it very easy to build a antenna from them. You would adjust this. This big a spacer, which is the 7 millimeter, would be for the highest frequencies. It would make the loop resonate at the highest frequencies. The smaller clips, like the one, let's say, would cause the loop to resonate at a lower frequency. So if you have a length of pipe, let's say 20 feet of pipe, like for the 20 meter antenna, and you can adjust these spacers so that you get the resonance at the bottom of the 20 meter band. The other thing on there I showed you was the tuning screw, which adjusts the spacing between that one last segment of pipe so that you can tune to different frequencies. This is one example of a machine. It's, again, 3D printed with a nylon screw. And as you turn this, you bring the pieces of tubing closer together, pipe closer together, or turn it the other way, you separate them further apart. It works a lot better when they're attached to the loop. But you can see here, as I turn this, it pulls them further and further apart. This is a very simple device, very easy to build. Anything could be jury-rigged to do this. This is a little bit more fancy version with a trough that holds it in place and a long screw, black screw here that moves it back and forth. And you can see you can get quite a bit of separation for this. You can pull that part of the loop, the tuning arm, further out. Now, also, sometimes I will use glue to hold the clips in place if I have a permanent kind of loop. So I'll use this goop type of glue, which works pretty well, but can be removed with some effort. We're going to switch back to the loop. Okay, I've got my antenna analyzer precariously perched here on the tubing. I hope it won't fall. And I have my hand on the tuning screw here. Notice that as I come close to the loop, it moves around a bit, so there's an effect of my hand on it. And by bringing the two turns closer together, I can move the tuning spot there. That's exactly on the bottom of the 40 meter band, 14.0 megahertz. And if I make it a little tighter, I'll go a little bit below the band. There we are at about 150 kilohertz below the band. And if I bring it up here and space them a little bit wider apart, the tuning goes up the band. And there we are at 200 kilohertz above the band. Here I'm going to set this with that's 100 kilohertz above the band. I'll set this to a 500 kilohertz range. Hang on. So that's 500 kilohertz. So there's 250 kilohertz to the right of that center line. And as I spread this apart, you can see that the tuning goes up higher and higher in frequency. And as I bring them closer together, you can see that it goes into the mid-range and tighten them down a little bit, and it goes to a little bit lower. So I'm able to cover easily the whole 20 meter band here. And by adjusting the spacing in this little part of the loop. So you can see how powerfully the spacing of the different turns affects the tuning. And so what you do when you make a loop is you adjust the turns with the tuning arm in a mostly inward position for the lowest part of the lowest frequency you want. And then you can bring it up and make sure it reaches as high as you need by adjusting the length of the tuning arm and the space this thing will move. Hope that's clear. So here are the ingredients to make. I'm going to pause for a second. Is that seemingly clear to everyone? I'll take that as a yes. Now we'll make one. Make this loop from scratch. This is a piece of PEX LPEX pipe. It's 20 feet long. It's extremely light. I can have no sweat hanging it on my little finger. Any child could pick this up. If this were copper, it would weigh quite a bit, but this is a very nice material to work with. It's light, and yet it bends easily, and it holds its shape very well. So I don't need to have multiple supports here for this type of a loop. It's just on one pole. And I'm going to make one of these from the parts. One of the parts is just 20 feet of pipe. Another set of parts here are 7 of these 5mm spacers. This is, I think, 4 of them, yeah. But I've got 7 of them over here, of the spacers. And then what I call a tuning screw, which is the machine, like this one down here, just a different version, that can precisely separate or move together these 2 arms, the tuning arm, to adjust the frequency, the resonant frequency. So the first thing I do is to take the pipe, and in this case, I really like loops that are just about 2 turns. So you can see this is almost 2 complete turns. They seem the most efficient compromise. I really get good results with the 40 and the 20 and meter versions. The 80 meter version, which requires like 45 feet of pipe, the 2-turn version is just a little bit too large, so I make that about a 2 1/3 turn as best I can. It ends up being about 6 feet. So right now what I'm trying to do is get this thing in a circle and get it close to 2 turns. And then I'll grab my spacing clips, snap one on, work around the circle here, snapping these on. Again, I have 7 of them, so I'll try to space them out pretty well. I played around with different size spacers and came to the conclusion that 5 spacers is probably, a 5mm spacer is a good number. The more spacers, the more stable the thing's going to be, so you could use more than 7 of them. And this loop, if I were to use 1mm spacers, would resonate somewhere way below the 20-meter band. And if I were to use 7mm spacers, it would resonate somewhere way above the 20mm band. So you've got almost all the spacers on here. One more here at the end. There's a lot of little tricks you can do. So if you're not quite at the resonant frequency you want, we call this end, and hang on, I've got probably 1 too many clips on there. We'll use 6 instead. I call this end the tuning arm, as you know, and it tunes by being pulled away or moved closer to the main loop. And it's good to get a nice smooth turn. You can also play around with this arm here, and in some cases I've had this arm move in 2 positions, one for the top end of a band, one for the bottom end of the band. So you can make adjustments over here. See how this is spaced a little bit large? Squeeze that down, you move the frequency lower. Anyway, that's part of it. Now, we're pretty close. This is the tuning screw, as I call it. That's probably the best way to put it on here. And it snaps. If this tuning screw on the already built loop has a little bit of glue on these 2 spots where it touches the pipe, a little bit of that good glue to hold it in place. So, all right, I bet you that took a whole of 3 minutes. I have this position here, so I can just remove it, put it on the floor. This is very light and easy to use. I mean, takes nothing to build, especially once you know what length of pipe to use and what type of spacers to use. Once you've got that, you can build these very easily. Now I'll hang it on the supports. I often do not get the spacers just right for the supports, but we can adjust that. Now I've got the tuning screw on the other side. It's not exactly the same, but let's take a look at where it resonates. I probably want to move this towards the center of the camera a bit more. Okay. We're a little bit high. So we need this to be a little bit closer together. And you can make some little adjustments like this to squeeze them together. Again, the more of these spacers you have around it, the more stable it will be. And now, here we go, right at the bottom of the 40-meter band. 20 meter, I keep saying 40, I'm sorry. At 14 point, in this case 065, but the bottom of the band. I hope you can see that at least a bit. And as I raise this up, pull the part further apart, you can change the frequency down or up. Frequency to cover the whole 40-meter band, 20-meter band, and then some. I keep saying 40, I'm sorry. I don't do much work on 20 meters, maybe that's why. Anyway, you saw how long that took to build, and you saw how difficult that was. Starting from scratch and having to figure out all the spacers and everything, that could take half an hour maybe, but once it's done, I mean, you saw how easy that was. That's what I wanted to show you. More later. Okay, we can pause here again. Is everybody keeping up? Is it making sense? You guys okay? Don't hear any complaints, I'll keep going. I took the antenna I just built, and put it out in my backyard here. You can see it's up, not that high, and connected it via some coax into my radio room, and I'm using Whisper, WSPR, with 80% of the time listening, 20% of the time transmitting, 5 watts. So let's see what stations hear us and what stations we hear with this 6-minute antenna. Those are the stations in the East Coast. The skip distance was long, so we got East Coast stations. This table shows the transmitting station on the 2nd column and the receiving station on the 4th column. So you can see in the course of maybe 2.5 hours that I ran this, we had well over 100. I don't know how many it was, but it's quite a few. That was 5 watts, fairly low power. Now this is my Elecraft KPA 500 amp and my 7300, ICOM 7300. And this is a SDR station in Pennsylvania. This is an East Coast SDR receiver. We're putting 300 watts through the 20-meter loop we built yesterday. Bands up and down. It's faded a bit, it's strong sometimes, but just wanted to show you that can run significant power. Don't recommend it. I mean, it's all experimental. We don't really know what the limitations are and exactly how the loops work. So do this at your own risk, but this is, as you can see here, 300 watts. And there's no sign of a problem so long as the SWR stays right. KF7, YRS testing. Testing 1, 2, 3. KF7, YRS testing. 300 watts single sideband. Okay, I'll pause there. So it's not a dummy load. It works pretty well. It has a little bit of directionality like all loops do, as far as I can tell. Still a lot of exploring to be done, but I do not understand how the currents and voltage are distributed. We'll go on, I'll show you the 40-meter loop and see what you think. Okay, it's the next day. We're back in the garage. Yesterday, I built a 20-meter small loop, and I've had it outside running it on Whisper and other single sideband CW. I ran about 300 watts through it, no issues at all. I don't know what the limits are. Please be careful if you decide to play with this. We don't know. We don't even understand exactly how the voltage and current distributes around these loops as compared to the classic loop where you have a loop and then a capacitor at one end and the feed loop at the other end, and we know that the high voltages are at the capacitor and the high currents is the opposite of the capacitor. I don't understand exactly how these loops work or why they can handle the amount of power they can. One of the limiting things for a regular classic loop, the regular design, is the capacitor voltage capacity, and you have to often use a vacuum capacitor, and even then the voltage limitations, the current limitations, and the power limitations are often expensive. If you get one that will handle 15 watts, it might cost $300. If you get one that will handle 100 watts or 200 or 300 watts, it's going to cost a lot more money. This costs $6. The parts in this cost $6. The pipe is 25 cents a foot. I make my own plastic parts out of a spool of plastic filament that's $20 per kilogram. So this is a $6 antenna that we built in 6 minutes yesterday. And I'll show you some of the data on another section. This is the 40-meter antenna. And yesterday, when we talked about the 20, I made a big mistake and kept saying this was 20 feet of PEX-LPEX pipe. It's actually 15 feet. This is made from 15 feet. This is made from 30 feet, so it's twice the length. It has a tuning arm similar to the standard tuning mechanism. Feed loop, that's the standard size feed loop, only it's a little more proportional for this size loop. And I'm going to give you a close-up tour now. Out again that this loop is very similar to the 20-meter loop we built yesterday. And you remember this was just a few minutes to wrap it up in the right size. It's a little bit more of a wrestling match with 30 feet of pipe instead of 15 feet. But it's the same thing. I have 7mm spacers here. I think there's 7 of them. A tuning arm with a pivot point. Tuning screw that moves the tuning arm in and out. And in this case, a stepper motor controller. But you know, this is made the same way. And this would probably take me, instead of 6 minutes, 10 minutes to make. Because it's a little bit more of a wrestling match to get all the pipe right and everything. It's, again, as I said yesterday, the 2-turn loop, which is a design I'm really liking. And I can get away with it up to 40 meters. At 60 meters, it's a little bit tougher to get the size that will, I'm shooting for a size that will fit easily in a pickup bed truck from the idea of emergency communications and going to remote sites. So this one is a 2-turn loop, works very well, The 80 meters, as I said before, is a 2.5 to 1/3 turn loop, and the 60 is somewhere in between those. I use 15 feet of pipe, and I kept saying it wrong yesterday for the 20. This is 30 feet of pipe. 35 feet I've used on 60 meters pretty well, and I started out with 40 feet of pipe for 80 meters, but Fred and others made the observation that that was probably a little bit short. So I've now go to 45 feet, and it works well for the whole 80-meter band. 40 feet was really 75-meter band. But the same thing, just the clips. In this case, they're all 7s, but if I switch them to 5s, then the frequency would be a little bit lower. So you can play around with that. The cost of these antennas, as I pointed out in another segment, is very little. The pipe is 25 cents. The parts are essentially free if you print them yourself. There's no need to use this kind of equipment, though. You can use duct tape. I mean, you could duct tape, you can hang this on a nail up there on the top, or maybe wrap some insulation around the nail and hang it on that. You could cut little pieces of wooden dowel or wooden blocks and put it between the 2 levels of pipe and then duct tape that together to space it. So, I mean, it can be made a number of different ways. It's a very simple idea. And as I said in another segment, I don't really understand why this can handle so much current, but it is very inexpensive for the amount of power you can put into this. A friend of mine, Mac, K8NG, on another one, which I can show you later, has put up to 750 watts into it. I stop at about 300, 400. I probably use 500 single sideband on the 80-meter loop on occasion. I think I've got a little segment for you with 300 watts in the 20-meter loop, but I wanted to point out that this is made the same way, and all of them are essentially made the same way, with just taking the appropriate length of pipe, and appropriate in quotes because your mileage may vary. You may want to use more or less. Capture area, the bigger the circle here, the more radio signals it's going to pick up. And the rounder the circle is, this is more egg-shaped. Gravity's had its way with this. These St. George hot days soften things up a bit. And so it's more of an egg shape. But you can actually tune it with a tuning arm, but there's many other ways to tune it. One of which is, the more close it is to completely circular, the higher the inductance, the lower the frequency. So this egg shape will have a little bit higher resonant frequency than if I were to carefully form it into a circle. So there's a lot of ways to do this, and I'll talk about some other ways in another segment. Okay, we're looking at the 40-meter loop. I have my antenna analyzer here perched on a little, the bottom support. Have a little bit of Velcro here and rubber bands to hold the bottom of this in place. This is the tuning screw, as I've called it before. This is the tuning arm here that moves in and out to tune it. In this case, the tuning screw is built into the base, so these are all one piece. The slide here that the tuning screw works on, and the support piece there. That's all one piece of 3D printed. Actually, it's two pieces, but they're glued together. What else is different here? It's the same feeding loop setup, so very similar, in fact, almost identical to the one we had yesterday. 3D printed the orange part or the red part, and then some 1/4-inch copper tubing wrapped in some electrical tape just to be sure. And then up top there's another support. It's just the support I had around here to hold up the top of the loop. The loops, because of gravity, it's sort of more egg-shaped than it is circular. I've used this loop for many times, many days, months. Checked into the beehive, and dozen times maybe. Lots of activity, and it's been in and out. I can set it up in a few minutes. One of the differences here, however, is the way that the tuning screw is adjusted. Rather than having a hand adjustment where I would turn the tuning screw like we had on this one, this hand adjustment here, this has a stepper motor and a stepper motor controller. This is the stepper motor controller board down here, and I bought it from a fund, it's not really GoFundMe, but a tech site for about $60, I think it is, but it's a very nice one. And this is a stepper motor here I got from Amazon for not very much at all. There's a coupling here. This is a jury rig system. I'll show you a nicer one on my 80-meter loop, but on the 40-meter loop, this is a bit of a jury rig system. But when the stepper motor turns, the turning is transferred up here to the tuning screw, which moves the tuning arm in and out and tunes the frequencies. And here, one of the nice things about this stepper motor controller is that it generates its own Wi-Fi hotspot. Antenna analyzer showing the resonance points, again a 1-to-1 SWR, very close to it. This is center line is the center of the 40-meter band. Stepper motor controlled by the stepper motor control board, and the stepper motor control board controlled by this Wi-Fi interface so that I can work from anywhere around my house. It makes it very easy to switch the frequencies and such. So if I turn this to the right, let's say if I want to go to a higher frequency, this should move to the right. I'm going to hit this button here on my phone, and you can see here the stepper motor is turning. You probably can't see that it's moving there, but you can see here on the antenna analyzer that it's tuning up the band. It's passing through the lower part of 40 meters. It's approaching the middle of 40 meters there. And I can adjust the speed here to whatever speed I want. I can slow it way down, which is sometimes good to do if you're fine-tuning. We just stopped right on, pretty close to right on the middle. Or I can really speed it up quite a bit. Let me go back here and just take it to 30 RPMs. And here you can see it's really moving. And this should be moving proportionally faster as we're tightening these two together, as we're separating them a bit, and the resonant frequency is climbing. So these are the whisper results I got with this loop back in last February. That's 6 out of 7 continents in one night. This is a single sideband. Got some RF into the shack because I was too close.
Zero traffic and a time.
You guys recognize this?
30 or 41 minutes and they 70. Checking in. Have a great day. Who's the other? Check in, guys. Any other visitors?
Kilo Foxtrot 7, Yankee Romeo Sierra.
Okay, King Fox 7, Yankee, Romeo, and what's the last character?
Sierra.
Yes.
Yankee Romeo Sierra.
Okay, you came up at Romeo Sierra. Thank you very much, and thank you. What was the other one?
This is the 80. I'm going to pause here for a second. I'm just going to go briefly over the 80-meter loop, which is very similar, and then show you some pretty innovative, unusual things. Hope everybody's lasting okay. And I don't know, any questions? Obviously, I'm not meant for Hollywood. 80-meter version of the loop. It's 45 feet of XL PEX wrapped in about 2 1/3 turns. Standard tuning arm, a screw on a stepper motor there, Wi-Fi stepper motor controller. The same, I think it's a 40-inch loop of 1/4-inch copper tubing that's being fed there, the coupling loop. It's getting to look a little small with this size, which looked really big with the 20. You can see here the size juxtaposition of the 20 and the 80 loop. It's a big difference. If you think that the 20-meter loop is about 15 feet and the 40-meter loop is about 30 feet, you might think that the 80-meter loop should be about 60 feet. And maybe it should, but I'm trying to keep the antennas to a size that can be transported in the bed of a pickup truck, and this is just about as big as it gets for that. Although, if you had to assemble one of these in the field, you could roll up the PEX tighter in a circle maybe 2 feet in diameter, and take the clips and everything, and then unroll it and wrestle with it. Needless to say, we built the 20-meter loop in just 6 minutes or so, 5 minutes or something. And the 40-meter loop is a little harder to build. This one's a bit harder, if only because it's just so big, you have to move it around. And this one has spacers that are much tighter as well, because when using less pipe, then sometimes you have to space it closer together to get the same resonance. The capacitance needs to be higher if the inductance is less. So the larger the loop. The bigger the loops are, the harder they are to use in the garage, because the metal around them and being so close to the ground does have an influence on how they operate. So again, this is 2 turns of the PEXL PEX on this side and 3 turns on this side. The tuning arm pivots from, in this case, I've got it pivoting from way up there, so there's no connectors on the rest of this down to where the tuning machine is. It's your standard feed loop and coupling loop, you might want to call it, and the holder at the top and the holder at the bottom. This one has a bit of a guide, a little bit of longer sides to guide the tube up and down. It's a stepper motor controller. Again, the stepper motor board and the stepper motor itself. And let me see if I can back out here a bit. So you can see there it's tuned a little bit to the bottom of the range, and I'm going to start the stepper motor turning. You can see the motor is turning. The arm is coming down a bit, and the frequency has gone off the top of the range. If I expand the window a little bit by expanding the scan width here at 200, you can see that as we go to the right, it moves up. To the left, it moves down. This machine uses a much smaller stepper motor. It's about half the thickness, maybe less than half the thickness of the one that I used on the 40-meter, because this mechanism has less friction in it. It's much easier to turn for the stepper motor. And it does a very nice job of adjusting the frequency, because sometimes when the loop gets hotter, it'll change a little bit. Certainly if it gets wet, it'll change a bit. And sometimes just a breeze or something will cause it to stutter a little bit in terms of SWR. So you want to build these things as rigidly as you can. Use a lot of spacers around them to hold it nice and in place. I've gotten so that they actually stay pretty good over a course of maybe need some adjusting every couple hours, or maybe even sometimes they'll last a day or so without needing any adjusting. But it's all how you build them, and then there's a lot more to learn, and there's a lot more you guys can teach me. Okay, this is another way of tuning that I just added this video. We have two loops here. I've called this a hinge loop experiment. And one of them has a coupling loop attached to it. When the two loops are at right angles, there's no interaction. When the two loops are in the same plane, there's a maximal interaction. You'll see here that moving the loops out of the same plane to right angles sweeps a 2 megahertz bandwidth. So this could be a multi-band antenna. This is a different way of tuning. Spare no expense for the equipment. My wife is pulling the string there. So taking that another step forward, if you rotate a loop inside another loop or outside the other loop, you can, every quarter turn will go at right angles, and another quarter turn will be in the loop, and another quarter turn at right angles, another quarter turn in the loop. So every revolution, you scan the band 4 times. So if you adjust your loops right, I've done this for the 40 meter frequency, and put it on a stepper motor, you can have a magnetic band scope. So you see the whole band, but you see it in a magnetic rather than electric spectrum. And if the thing doesn't fly apart at first. Mine is not scanning fast enough to get a high resolution on the sound, but the idea would be you would have a band scope, you could click on a signal, and the computer would stop it there, and you would zoom in on that signal. So take a look at this. I think it's pretty interesting. You'll hear the audio. Let's see how long it takes this thing to go. We're almost at the end, guys, so hang in there just a little bit longer. I think you'll find this one interesting. All right, there we go. This is the gear that turns the outside loop around. This is 3D printed herringbone gear, stepper motor driver, stepper motor. So this sits at the base of the antenna that I'm about to show you. There it is, turning very slowly. Every quarter turn sweeps the band. Speed it up a bit, really speed it up a bit. It's about to fly away. This is what comes out of the SDR. It's scanning each one of these white lines is a scan of the whole band. We're sitting here on top of someone talking, and you can almost make out what he's saying. The point there was that if we could spin faster, you would sample at a faster rate. You should be able to pick up the audio from each one of those signals, click on it, listen to it, and then stop the turn at that point. So unlike the other band scopes, this is the magnetic aspect of the signal as opposed to the electric aspect of the signal. So there's a bunch of things. This is the last slide, so hang in there. There's a number of things to do with the loops that increase ease and stability. I have made multi-band loops. I think that'd be a good thing to do. There's different ways to tune them that would work with multi-band loops, including I've made one that was a big watch spring. So it didn't just have a tuning arm. The whole thing coiled and uncoiled. So everything moved apart from each other and everything moved closer together. And that covers a lot of range and frequencies. The variometer is interesting because actually there are 2 resonances in the same structure. As the variometer turns, one resonance moves down and one resonance moves up in frequency. The down is due to capacitive changes and the up is due to decreases in inductance. And I've got evidence for that. We'll have to wait for a while. Other things I find interesting, there's something called skin resonance. There's a nice, very short little 3 sentences or so in a website about a guy who worked at Oak Ridge National Laboratories working on superconductors. Dr. R.C., I think his name is E.C. Jones. And he has lots of publications on superconductors, and he's a ham. So he took a 2-foot tall superconductor pipe and he connected it to his amateur radio at 1.86 megahertz, 160 meters. And in its non-superconducting state while it's at room temperature, he was transmitting on it, and he got a carrier S meter reading of S1 at a remote receiver. As he started to pour liquid nitrogen onto the antenna to cool it, when it went to superconducting, the signal went from S1 to S9 for a 2-foot length of superconducting. So that promise, I'm looking for various ways to make low frequency antennas small. And that's one of the possibilities. The other one is this velocity of propagation. We all know when you cut a dipole, you have to account for the insulation on the wire and the velocity of propagation. You have to cut it shorter than you would just a solid piece of copper. Well, some materials like distilled water have an 11% of normal propagation velocity. So an 80-meter half-wave dipole would only be 14.3 feet long if it were put in purified, very pure distilled water. So these are some ideas I like to play around with, and that's going to be the end of it. Love to take questions. Hope I didn't go too long. Really appreciate the opportunity to talk about this. And I'll just shut this down. Go back to screen sharing. It stopped. Everybody still alive?
I have a question.
Good.
Yeah, have you tried doing multiple turns?
Yes. Some of them I've gone up to 3 turns. It seems to me that they're less efficient when I do that. I think it's decreasing the capture area. So I think you still, size still matters here. And that's why I sort of like the 2-turn. But I have done a complete 3-turn. And I took 60 feet of pipe and wrapped it 3 times in a triangle type bundle. Just zip tied them together, no spacers whatsoever. And that was running on 160 meters. And Kelly, KV7V, and I were talking back and forth on it. It wasn't real impressive. It wasn't as good as the 2 turns or 2 1/3 turns loop. But there's so much experimenting to do here. I mean, this isn't in the literature. There isn't any information I know on it. I would love to encourage some of you guys to give it a try.
It looked kind of like a transformer to me, the way the antenna works.
Yeah, certainly there's a transformer aspect to the coupling, but you have to imagine that the capacitance is distributed around the loop, and the inductance, normally you'd want the capacitance at one end and the inductance at the other end. I mean, I've got a little video here that shows what a normal loop, how the current flows, but I don't understand it, and I'd love input. Any other questions? And any suggestions on how it could be working would be gratefully appreciated. I know a lot of you guys. It's nice to see you, and hope you're all doing well. It didn't get blown away today. It was pretty windy down here.
Have you experimented with the difference between the coupling loop and the main loop?
Yes, but not extensively. I have done that on the 20 meter, made a smaller coupling loop and angled it in different ways. One of the things that's interesting to me is normally you'd feed the antenna opposite the capacitor, but it doesn't seem to matter where you feed this antenna. You can rotate it on the coupling loop, have the coupling loop on the main support, and then rotate the antenna, and it seems to still give you a 1-to-1 SWR. So it just seems like it's just equally distributed around the loop. The minimal loop I've used has been maybe, instead of a complete overlap 2 turns, maybe 1 1/3 turn. So it only overlaps for a segment of the tuning. And in that case, it acts more like a classical loop where you put the coupling loop opposite, and the 2 turns at the bottom that are the capacitor seems to work that way too.
Lee,
Yes.
I just wanted to comment that the lecture was just fantastic. You might consider we need to have it in QST. I thoroughly enjoyed it, and the folks enjoyed your lecture. You ought to check out Lee's Ham Shack. He's got all kinds of neat goodies, and it was very, very educational. And good to see Eric Nelson, you and I on with us. And I want to thank Eric for introducing me to you. Very good.
Well, thank you. Now that this Zoom presentation is made, I might try to give it at the local St. George Club too, just to see. So appreciate you guys inviting me. It really was something I really enjoyed doing. I was surprised how much fun I had putting it together.
Hey, Lee.
Yes?
Yeah, have you tried stacking the loops side by side instead of inside each other?
Yes. You can stack them side by side, and as they approach each other, you start to get lower and lower frequencies. So you can adjust the tuning by two loops that would be like this and moving them back and forth as they approach each other. Interestingly, if you have a main loop that you're like the transmitting loop, and you have a one-turn loop for the inside, if that inside loop is broken, so it's not a continuous circuit, it's just a broke, it's a piece of pipe that you didn't connect the ends to, then when you rotate it into the plane, the resonance goes down. If you jumper that so that it's a complete conductive circle and you rotate it into the plane, one resonance goes down and another resonance appears, it moves up. And it turns out that when you have two inductors in the same plane in parallel, when you have inductors in parallel, they decrease the inductance. So I put my inductance meter on it and rotated the loop up with the completed circle with the broken circuit. And you could see that with the completed circuit, the inductance of the main loop dropped quite a bit as I rotated the second loop in. So there's something complicated going on. And in some cases, I can watch I made two 20-meter loops identical. And I fussed with them until they were just right on top of each other. And then I did the hinge experiment. And I saw two resonances starting off at their resonant frequency, one going up and one going down. So I'm a biologist, guys. This is fun, but it's stretching my engineering abilities, which aren't that hard to stretch.
AR7KR question.
Go ahead.
Two questions. One was what is your mast made out of? And the other is, do we know what polarization this is? Is it vertical or horizontal, or what the polarization is?
It should be a vertical polarization if it behaves like other magnetic loops. That would be, and that's with vertical polarization, you can deploy them pretty close to the ground without an issue. With horizontal, they have to be a significant fraction or wavelength up. The support post, I've used PVC, I've used a number of things, but the ones I was showing was that military 4-foot sections that slide together, they're fiberglass. They're used for holding up camouflage net and such in the Army. They typically sell very cheaply on eBay. So that's what the support post was, but I've used all kinds of things. And I've even hung them on a branch in a tree. So, I mean, without any support post, I just hung them on a branch and hung the coupling loop there too, and can use them that way. I've often thought I should have a post with just little pegs on it. And this is the peg for the 20-meter loop, and this is the peg for the 40-meter loop, and this is the peg for the 60-meter loop. And have one coupling loop on there, and I'd be good. There's a lot of things to do here and a lot of ways to make this better. So I look forward to any suggestions and anybody else trying it. Fred, I was so happy when Fred came and got involved and that it's working for him.
Yeah, I have a bunch of the PEX out PEX, so if people want to try an experiment with it, I can get it to you. I gave some to George, and I've been using it to check into the OrcaNet, and probably do some more prototypes, maybe make some a little bit bigger and things like that. But it's been working. I've been able to check into Oregon, and yeah, it's been working great. It is. You did mention it's a little bit directional, so you have to kind of make sure the loop is kind of aimed the direction that you want. So I can't hear California very well, but I can get into Oregon and Washington, places like that. So yeah, no, it's a really interesting material. And yeah, I've been looking at making magnetic loops and looking at the price of capacitors. I was kind of kind of disappointed that I didn't have that kind of money available. And this basically got rid of that problem and solved it. So you can basically make the loop without having to worry about spending $100 on a capacitor. So yeah, I'm glad you shared it with me. So thank you, Lee.
Yeah. Yeah, if you spent $20 in one of these, you probably paid too much.
Hey, Lee, if you make the loop larger in diameter? Would that give you a broader bandwidth?
I don't know. I don't know. I think you'd have, I don't know. Something I need to do. I've seen different bandwidths, and I've seen different bandwidths with different coupling loops sometimes. With a 20-meter bandwidth, I made a small loop, and when I got it, it wanted to be right in the center of the loop to couple with a 50 ohm connection. And as I turned it out of the plane of the loop, I could make the bandwidth more narrow or more wide. So I'm not sure what was going on there. Again, I know they work, and I've made a few of them, but there's still a lot more exploring to do.
So most of these have been made out of the 1/2 inch, right?
Yes, all of the ones I've made are made out of a 1/2 inch. There's been the suggestion that the 1 inch would be better for radiation, but for efficiency, but it's just pretty heavy and awkward.
Yeah, I was kind of curious if you'd done that. Yeah, for an 80, that would be kind of heavy, but it's kind of curious because that kind of goes to Ed's question too. If you use thicker versus thinner wire, you can change the bandwidth. So I wonder if the 1 inch would be different.
Yeah, Eric and I split a 100-foot roll of the 1 inch once.
Yeah, the greater the surface area, the lower the resistance for the RF.
Right. That's an interesting comment because Rudy Severns, who's an antenna expert, published a lot in a lot of the QRX and different magazines and such. He's published supported the notion that as a ribbon conductor gets down to approaches 2 skin depths at the frequency you're interested in, the inductive reactance goes to 0, and all you have is the regular resistance of the aluminum or copper. So a lot of the inductance is due to current flowing up on the outside edge and then flowing back in the center. And as you get closer to one or two skin depths deep, that center part no longer goes, the eddy currents no longer flow, and the resistance drops to, the inductive reactance drops to 0. So Dale Parfet said, I never heard of that. He said, I think that'd be called skin resonance. And the PEX-L-PEX we have, which is a 200 micron thick tube, should have a resonance, should have about 2 skin depths at about 500 kilohertz or so. 420, 500, I forget the exact number. And I played around with it. I made a big coil of it and looked at the impedance and the reactance, inductive reactance at various frequencies. And indeed, there was a big change right at that 2 skin depth level. So, you can imagine making an antenna with a specific thickness of conductor that was for that frequency. And that would be almost, but not a superconductor, because you'd still have the actual resistance of the aluminum or the copper or whatever you made it out of. I bought a whole bunch of copper tape and pool noodles, swim noodles, those things kids float in pools with, and little wooden dowels to hold them into a big circle. And then I'm using copper tape as the skin effect, as the conductor. Trying to see if I can understand that skin effect and the loss of inductive reactance at a certain thickness. Certain metals can be made into very thin foils like gold and such. And I could imagine if you wanted an antenna for a very specific frequency, like you were somewhere and your agency, your company, your whatever communicated on a specific frequency, then you could probably make an antenna with a foil, or even ideally a tube that would be very effective at that given frequency. Sorry, that's just something I don't have time to go into very well, but I could send you some references.
Yeah, I know that the greater the surface area, RF travels along the surface of the metal, not in the inside. So the greater the surface area, the lower the resistance. So for low frequencies, that larger tubing might be a better choice.
Yeah, that might be, but the skin depth is still way smaller than the 200 micron thickness of the aluminum we're using. So I think you'd have to get to lower frequencies than we're using. And the inductive reactance at lower frequencies isn't that great. One of the nice things about the PEX-L-PEX is that the aluminum is pristine and encased in polyethylene, so it doesn't oxidize on the surface. So the surface is protected from oxidation that's been thought to interact with the skin effect and cause resistance as well. I've made a nice loop hourglass antenna for 2 meters with this stuff too. It works pretty nice for that too. Mac K8NG also made one with the Pexel PEX for 2 meters. That's what he uses on the Kelly's net.
Interesting stuff.
Yeah, it's a great hobby to have because there's just 1,000 different interesting directions you can go in.
Well, what's nice is it has characteristics like the copper tubing where you can bend it and it will keep its shape too, versus like wire which kind of goes floppy on you.
Yeah.
That's another nice thing about it too.
Yeah, and it's so light that you know, I can, if I tried to hang an 80-meter loop built that way, and it was a regular plumbing tubing, I probably couldn't pick it up.
Yeah, the only limitation I can see of this type of antenna is the bandwidth. If you overcome the bandwidth limitations, you got it licked.
Yeah, but that's thought to be part and parcel of the small antenna for efficiently radiating, that you sacrifice bandwidth for efficiency. But that's why I sort of like that scanning technique, where we scan those other frequencies repeatedly and quickly. And you know, if you sample a waveform at about twice its frequency, you can reproduce the waveform, and that includes audio. So if we were scanning at a rate that was twice the audio frequencies, we should be able to listen to individual audio at sampled audio at some points along that band scope. So
that's awful fast rotation.
Yeah, but we were getting close there with just 20 RPM or something like that I was getting. So every rotation gives you 4 scans. So you can.
Well, does anybody have any other questions for Lee?
Thank you for the presentation, Lee. I liked it a lot.
Oh, great. It was a lot of fun. I really appreciate it. I've been doing this for a while, and I'm just glad to talk to somebody.
That was great. Thank you for coming up digitally and helping us out here. And I've recorded this, and so I see Terry's on here. Maybe we can get this put up on the website for other people to take a look at too. That'd be great.
Okay. I don't want to go viral.
You'll be viral in the Cedar City and St. George hams.
That's good enough. That's good enough.
Okay, well.
Thank you.
Thank you very much. George, did you have a question? So you went unmuted there. L7BX?
Just say hi to George.
You have an audio difficulty. Well, anyway, again, I'd like to on behalf of the Rainbow Canyons Amateur Radio Club and everybody who participated, I'd like to just say thank you very much for the presentation. It was great. And I have a bunch of the Pexel PEX. So if somebody wants 45 feet or whatever for 80-meter antenna, just let me know. And yeah, it's not hard to play with. It's really easy. You'd have to watch the wind, though. We had that windstorm a couple weeks ago, and that really wonked out my my tuning. But it only takes a few minutes to get it back, so that's not a nice characteristic of this. So even if it gets blown around, you can put it back.
I accidentally opened my garage door with the 80-meter antenna in there, and it just about chewed it up.
Yeah. So, well, 7-3s, everybody. Good night, and have a wonderful rest of the week. It's Tuesday now, I guess. So thanks for joining us tonight.
Thanks, Fred. Good night, everybody.